All right, here is our lesson on concentration stoichiometry, otherwise the stoichiometry that goes along with the lab technique of titration. So we're going to start this off by defining what a titration is. And if we were still in school, what we would be doing is we would be titrating your aspirin in order to figure out how pure that aspirin is compared to name brand aspirin. Maybe we get to do that next year. Let's cross our fingers. So let's define titration. Titration is the slow addition of one solution of a known concentration. We call that the titrant, to a known volume of another solution of unknown concentration called an analyte, until the reaction reaches a point where all the analyte has reacted. This is usually indicated with a color change. So in order for us to figure out what the concentration is of the analyte, we have to figure out how much titrant we need to add and figure out from there the moles of titrant added. From there, we'll get the moles of analyte in the solution and then get the actual volume and concentration. So that sounds like a lot, but I'm going to show you it's not as much as it sounds like. Before we show what that calculation will look like, I'm going to show you what the setup for a titration would be if we were in the lab. This is a burette. A burette will add very small amounts of titrant to the analyte at a time, so you can get a very precise reading of how much titrant you need to add to the analyte. This is called stopcock right here. This specifically controls the flow of titrant into this flask. And then notice that there's a color change going on here. We usually use some sort of indicator. If we were in the lab, you would have been using the indicator phenolphthalein. And when you get the color change, you know you've added enough titrant to react with all the analyte. So this is how we would set this titration setup. And this is where we'd get our measurements in order to do some concentration stoichiometry. So when we're doing concentration stoichiometry for titrations, we need to think of four things. Thing number one is we have to decide what type of reaction is happening between the titrant and the analyte. Second thing we need to consider is what products will be created. Third thing we need to consider is what variables we're looking for. And I'm going to show you a nice little way to organize that and set it up. And I have to make sure my units match. I have to make sure my volume is in liters. I have to make sure my concentration is in moles per liter, and so on and so forth. So on the next slide here, we're going to do an example problem. Okay, so the first thing I'm going to do here is try to identify what type of reaction is happening when I've got a volume of 0.200 mole per liter. And remember, the dm to the -3 means liter, potassium hydroxide solution. And it's going to be reacted to neutralize 25 CM3, and the CM3 is milliliters of 0.200 mole per liter aqueous sulfuric acid. So remember, step one is to figure out what type of reaction I've got. So here we go. We're going to start by writing, excuse my penmanship, we're going to start by writing my two reactants. So here's my H2SO4, and it's going to react with some potassium hydroxide. And hydroxide is on your polyatomic table. It has a -1 charge. Potassium has a +1 charge, so those charges balance each other out. So I notice here I've got two ionic compounds. And so what I can do is I can see that it would take on the form AX, where my X here is my anion sulfate from my polyatomic table, BY. And now I'm ready to predict some products because I know my general formula is AY plus BX. So A in this case is going to be the hydrogen, and the Y in this case is going to be the hydroxide. And notice that the hydroxide has a -1, so hydrogen has a +1, so they cancel each other out. And HOH, well, that's 2 hydrogens and an oxygen. Well, that's just water. And then I've got some potassium mixed with some sulfate. Sulfate from my polyatomic table has a -2. Potassium has a +1. I flip the charges, make them subscripts. And there you go, just such as that. So my last step here is to make sure my molar ratios are correct or balance the equation. I need to have 2 potassiums. And now I've got 4 hydrogens and 2 oxygens. So I'm going to put a 2 out front here. So now I know what reaction is going to occur. It's a double replacement reaction. And the subset of this is an acid-base reaction, because I know that I've got sulfuric acid. That's my first context clue. But one of the products is water, which is going to show me that a neutralization has occurred. So I've got an acid-base reaction. Okay, so now that we've got our balanced chemical equation, it's time to look at some of these measurements. I'm looking for a volume. Let's turn back on my pen. I'm looking for a volume of potassium hydroxide that has a concentration of 2.00 moles per liter. Again, remember that DM-3 is moles per liter concentration. So I'm going to come over here to my unknown. In this case, I don't know the titrant. And I'm going to say its concentration is 0.200 moles per liter. And I can use capital M to represent that. And I don't know the volume. And then I do know that I've got 25 milliliters of sulfuric acid. That's a volume. I also know that I have to change milliliters to liters. So I'm going to take that decimal and move it 3 places over to the left. And I know my volume is 0.025 liters. I didn't introduce my little chart setup here, but it's an easy way I use to organize what I know and don't know. And I also have a concentration of sulfuric acid to be 0.200 moles per liter. So now, if you notice, I have enough information in my known category to get my moles of sulfuric acid. So what I'm going to do is I'm going to use that concentration equation that we did in the third learning target to get the number of moles. So I've got C equals N over V. And to get the moles, I can say C times V equals N, isolating my variable. I got the 0.200 times the 0.025, and that's going to give me 0.005 moles of my sulfuric. Now, I rounded to 1 sig fig here because there's 1 sig fig in my concentration. So 0.005 moles of sulfuric. So now what I can do is I can do my stoichiometry. And now if you have your mole highway out in front of you, you may notice we're right there in the middle of the mole highways, moles of the given to moles of what we want to find. So I've got 0.005 moles of H2SO4. And I'm going to times that by, there's 2 potassium hydroxides, because that's what I'm trying to find, to every 1 H2SO4. Where did that ratio come from? Well, once again, my balanced chemical equation. 2 potassium hydroxides to every 1 sulfuric acid. And so if I multiply these things out, I'm going to get 0.010 moles KOH. And I am so close to being done, because now I've got moles of KOH, I've got a concentration of KOH, I can use that concentration equation that one last time to get my volume. So what I'm going to do here is I'm going to say C equals N over V. I'm going to use that triangle that I taught you in the previous learning target to rearrange and say N over C equals V. So 0.010 divided by 0.002. And I solve that out. I get 0.05 moles, or excuse me, liters of KOH. Let me rewrite that really quickly because it's kind of messy for you. So once again, I took the moles of KOH and I divided it by the concentration of KOH, and I got 0.05 liters KOH. So because my original volume though started in milliliters, I'm going to convert that back to milliliters by moving the decimal 3 places over to the left. And so I will find that my answer is now 50 milliliters. So what does this exactly tell us? If I go back to that diagram that I had, that means that in here, the amount of sulfuric acid would have been completely neutralized with 50 milliliters of the potassium hydroxide that is put into here. So this is your first introduction to concentration stoichiometry. And I know you're going to have questions because there's a lot going on here. This builds on almost every single topic that we've learned since October, minus the Lewis structure intermolecular forces stuff. So hopefully this makes a little bit of sense to you. Please message me if you have questions, and good luck.